Hello everyone, now let's get started. So my name is Natalie Alima, I'm obviously Australian, apologies for the accent. I'm the Mycelia Kanye West Adidas girl from the intro before.
I miss the old Kanye.
Before I get into my background and my presentation today, I'll just give you a brief background about my expertise within the field. So I was originally trained as an architect in Australia. I then did my master's at Ike University in Barcelona, and it was there that I really developed this passion for biological materials and robotic fabrication. So when completing my master's, I returned back to Australia and started working for quite a well-renowned architecture firm designing multi-residential buildings. So on my first day, I hated it. I remember thinking, where are the robots? Where's the parametric design? Where's the innovation? I don't understand how, the real world of architecture is using quite antiquated design techniques. Where's the AI? So I lasted about 2 years there, and I thought I really want to return back to my passion for R&D, material development, and computational design. So I returned back to academia to teach and to start my PhD in microbiological scaffolds and how to apply that technology to the architectural industry. So when completing my PhD, I started working for Yeezy and Kanye West, no questions about that one. And now I work for the broader company of Adidas as a product designer. And what I'm currently trying to do is take these innovative techniques to the commercial industry. So thinking about how do we actually mass produce technology, what are the costs of this technology, and how do we solve these problems that we face when mass producing a product. So my research really involves this fusion of computational design, living materials, and robotic fabrication. And what I'm really interested in how to actually create a feedback system between these three elements. So how can robotic fabrication be influenced by biological growth? How can computational design orchestrate biological growth? And how can biological growth inform computational form? So the first project I'll present is called Bioscaffolds. This involves the robotic reading and infusion of a liquefied culture of mycelium into a series of biodegradable scaffolds. So for those who are unaware, mycelium is a fibrous root of a mushroom, so that drink that we all drank yesterday. That wasn't from me, by the way. So its chemical characteristics include its ability to absorb toxins from water and its ability to act as a natural binder between organic materials. So I would say I'm quite a multidisciplinary designer. Yes, I was trained as an architect, so I've always been quite fascinated with the scientific industry. It's really the forefront of incorporating living biological materials and robotic fabrication. So innovative technologies such as printing artificial organs, tissue engineering, and bioprinting have always fascinated me, specifically the medical bioscaffolds. And why that's really fascinating is because they 3D print a temporary formwork, insert living cells, and then the living cells biodegrade the entire geometry, adopting its entire form. So then I thought, okay, so how do we take this methodology of biodegradability and biocompatibility that's occurring within the scientific lab on the micro scale, and how do we apply that to the architectural macro scale? So how do we actually apply these techniques to design and to architectural buildings? So similar to the methodology of the bioscaffolds, mycelium is actually able to biodegrade through a range of fibrous filaments in order to seek nutritious substrates. So we commonly in nature see mycelium or mushrooms growing on rotten woods within the forest. So mycelium is attracted to the fibrous properties contained within wood-based products. So doing this research and referencing what's happening within Mother Nature, I thought, okay, how can we apply this existing technique or this natural technique and apply it to the robotics industry? So here you'll see a 3D printed scaffold made out of a customized wooden filament. And on the top, you'll see mycelium grown within a brick shape. So what I've done here is I've extracted the mycelium in this syringe over here. And what I'm currently doing here in this image is I'm injecting a liquefied culture of mycelium into this 3D printed scaffold. So as in nature, over time, the mycelium actually began to grow over the wooden scaffold and biodegrade this entire form, so started eating through the form and adopting its entire geometry. So this methodology of an organism eating through a structure, adopting its entire form, was something I really became interested in and developing throughout my PhD. So another thing about me is I'm obsessed with robots. Everything that I do manually, I try to do automatically with a robot. So what's really interesting here is, when we think of robots, we think, something acting really fast or a robot lifting something really heavy, but we really rarely think of robots as something slow, patient, and on the granular level. And that's something that I was really interested in. This is a term that I've coined slowbotics, of how can we, hack into a robot and use it to intervene with biological growth over an extended period of time. So how can a robot perform tasks that humans would ordinarily get tired from? So how can, instead of me monitoring the life of biological growth over 3 weeks without sleep, how can a robot monitor the growth of mycelium over an extended period of time and intervene accordingly? So what you see in this image here is the robot injecting a liquefied culture of mycelium into the biodegradable 3D printed scaffold over here. And what's actually happening is, through an attached Arduino sensor, which is a bit hard to see in this image, is the Arduino sensor is monitoring the life of the organism through color detection. So mycelium, when it's in its thriving state, has a white flush exterior, but when it's in its dying state, it has a brown, very distinct color. So through machine learning and color detection, the robot can now detect which areas of the scaffold is the mycelium thriving and which areas are dying, and then inject additional mycelium culture accordingly. So over time, here's a close-up image of the wooden scaffolds. The mycelium is growing throughout the geometry of the wooden scaffolds. And what's interesting about this image here is that because this scaffold is quite lattice-like and feather-like, the mycelium is being orchestrated to grow vertically along with the structure. So this idea of how can humans hack into biological growth and grow it in bespoke patterns. So here is an image a few weeks later of the mycelium starting to consume the entire scaffold, and as mycelium does, start to bloom and fruit mushrooms, which was quite an expected surprise. And here's an image of the mycelium over a 2-month period completely biodegrading the scaffold and showcasing its function in nature. It only occurs through robotic intervention and computational design. So this idea of how to combine those 3 elements and generate something completely new. So aside from robotic intervention, I started to think, okay, how can computational design orchestrate biological growth? So what geometries does mycelium like, and what geometries hinder the growth of mycelium? And through rapid experimentation and testing a few geometries, I discovered that mycelium is most attracted to quite porous geometries, because porous geometries allow the mycelium to seep through its internal walls and biodegrade the structure at a more rapid pace. And here's just an image of the scaffolds being incubated with mycelium, and the mycelium starting to grow throughout the geometry. So similar to porous systems, mycelium is also attracted to lattice systems, as it's able to consume its nutrients at quite a rapid pace. So with this knowledge of which geometries hinder and which geometries encourage biological growth, I computational designed a series of heterogeneous skins. And the point of these heterogeneous skins is to, at certain anchor points, encourage biological growth at certain points and then discourage biological growth. So again, creating this orchestrated sense of biodegradability, but also fossilizing the growth of mycelium. So for example, as you can see here, this little alien creature over here, is that the pink area is the smooth area intended to hinder biological growth. And then the fibrous antennas on the sides are intended to encourage biological growth. So as you can see here, the geometries more from lattice systems to porous systems to smooth surfaces to really generate the sense of a timeline of growth and decay. So my design process is definitely the pursuit of non-indexicality. I think a common, I wouldn't say problem, but a common topic with computational designers is when a computational designer looks at an image, we can trace the image or the form back to the algorithm. For example, if someone used Voronoi, I can say, you use the Voronoi algorithm. So I think a really important aspect of computational design is to begin to fuse softwares together. So I personally go back and forth between ZBrush, Grasshopper, Houdini, Rhino. One, because it's the pursuit of non-indexicality. So what I'm trying to do is move back and forth between softwares to blur indexicality. So it was really hard for one to pick or detect how the geometry was generated. One, because it begins to create a sense of ambiguity of how the form is derived. And two, because you start to work with this idea of emergence. So my design aesthetic is definitely amplifying the alien to really generate forms which, people don't know where it's from or what it is or how it's generated. Is it natural? Is it artificially made? So this is definitely my design aesthetic that I try to bring to the commercial industry. So as a science buff, I try to bring this idea of how to morph physical experiments within the computational realms, but using algorithms. So similar how a plant is manipulated through, a plant growth is manipulated through sun and humidity, how can we code external parameters to grow digital structures? So as you can see here, I'm manipulating the algorithm to generate these complex lattice forms that mimic the growth of coral formation. So scale plays an important factor within my design process. So here, the digital strands bundle at the base for stability and then branch off to individual wispy hairs towards the end to encourage mycelium growth. And again, I'm really interested in this idea of blurring the boundaries between the natural and the artificial realms. So when people view these geometries, they think, is this something found in nature or has this been computationally generated? So here's just an image of these forms that have been 3D printed. I label this series the bioscaffold series. And what I'm quite interested in doing is generating an architecture for the non-human. So these 3D printed geometries are intended for biological growth. Just a few more of these geometries. And as you can see here, just a close-up on one of the geometries is the lattice system, morphing into a smooth surfaces, which morphs into a porous system to encourage biological growth at certain anchor points. So this is the 3D printed scaffold pre-mycelium inoculation, and this is during the biological growth process. Same for this image here. This geometry here was intended to really encourage biological growth through its lattice formation. And as you can see here, the biological growth being directed through the computational pathways that I set it through. And what's really interesting about the geometry is I found that the organism, I found that the mushroom blooms according to the computational pathways that you set it to grow. So you really create this really nice harmony between the artificially made and the natural grown. And that's the relationship that I really try to embody throughout my work. So this second project that I'll show, so those geometries that I just previously showed were about just printed on a regular desktop 3D printer, so they were quite small. Then I thought to myself, okay, how can we take this research and apply it to the larger scale? So how can we take this research and apply it to architectural buildings? So this next project that I'll show is 3D printing biodegradable wall panel systems with mycelium insulation. So when we look at existing wall panel systems within architecture, they're commonly made with that foam toxic material for insulation internally. So how can we reduce material and create a more sustainable approach to absorb sound? So this wall panel system is intended to replace existing wall panel systems made with synthetic foam, except here the wall panel system is 3D printed and mycelium is used as a internal core to absorb sound within the wall panel system. So here's just an early prototype of this project. The skins was 3D printed out of PETG and mycelium grown inside to give it additional stability. And of course, mushrooms growing after an extended period of time. So computationally, I used a swarm algorithm to generate these quite reptile-like skins. And the purpose of these skins was to give the organism a geometry to latch onto and so it can adhere to the 3D printed skins. So another thing that I really love about robots is I feel like you can hack into any existing robot that's utilized for an existing application for something completely different. So for example, the Cooker robot is commonly used to assemble cars, but then I thought, okay, how can we use the Cooker robot to actually 3D print large-scale geometries, because it does have that height and that robotic reach. So here is just an image of the Cooker robot 3D printing the wall panel system. And this was about 2 meters high. Yeah, convert that into American. So that was originally utilized, utilizing plastic. So plastic is obviously something I'm trying to avoid within my work. So advancing this research even further, and I began to think, okay, how can we actually 3D print large-scale 3D printed wall panel systems out of a wood-based filament? So here is just some early prototypes of the 3D printed skins with the mycelium growing internally. And what I'm trying to do here is to really reduce the amount of material being used. So as you can see here, the skin is actually really quite thin and delicate, but it's the mycelium that really provides it with its structural stability. And then again, just testing various geometries to achieve various aesthetic biological growth. So here you can see, it has that quite thick foam-like consistency, but here it has that really nice wispy aesthetical growth. So again, just playing with geometries to see what type of mycelium growth we can achieve. Again, we have geometries that promote mushroom growth and then have that really nice wispy aesthetic. And here's just an image. This research is currently ongoing of the Cooker robot 3D printing the wood and filament structures, and completely eliminate the need for a structural host system. So now what I'm currently doing is 3D printing the organism directly, using a mixture of clay, paper pulp, mycelium, and hemp fibers. And the reason for the clay is that it provides the organism's structural integrity when it's being extruded from the robot, and the additional fibers, such as the paper pulp and the hemp, provide the mycelium food to absorb so it stays alive throughout the process. So thinking about how we can actually apply this to architectural structures, this is just a render, but this idea of creating temporary architectural structures made out of nature. Within architecture, we obviously build buildings for them to last 100 years, but I believe there's also a niche to build temporary structures. So this idea of how can architecture completely biodegrade back to the earth and leave no trace of its existence. So these initial prototypes were 3D printed from the UR10 robot. So this is the mixture I was speaking about earlier with the clay, the mycelium, and the hemp fibers. And here's just an image of the mycelium growing. And what's really interesting about this process of 3D printing with mycelium is that the form keeps growing after you've 3D printed it. So it's not like your standardized PLA 3D printed form. So here's just an image testing various draft angles and geometries of how the mycelium can grow once 3D printed. And this is a structure that we 3D printed with that organic medium I just previously mentioned. And just some images showcasing that. So I'll briefly touch on how my methodology of how to bring this innovative, futuristic research to the commercial industry. So within the commercial industry, there are a lot of limitations, including costs, durability, scalability. I work within Adidas, so we need to, within a few weeks, rapidly produce 6 million pairs, and that's obviously very difficult with mycelium and biofabrication. So currently, what we're trying to do within the company is to look at made with nature products such as kombucha and mycelium. And how to apply them to shoe design, whether it be certain components with the shoe, whether it be through packaging or the upper or the tread, so targeting specific areas within the shoe. So here's just an initial prototype that I've been creating of a mycelium sole. I left the mushrooms on here just to showcase that, yes, it is real mycelium. So this is just a initial prototype that I'm currently creating. Again, with the mushrooms growing. And I personally think that's really important. I've read a few pieces of literature how the human foot actually wants to be connected back to Earth. We used to all walk around barefoot. So how can we really generate that experience back again of connecting the human foot back to nature? So currently what I'm doing is, excuse my ugly feet, is thinking about how to create made with nature products to not only be sustainable, but also bring a sense of calm back to the human body. Here's just some and more images of that, of how to combine the mycelium bottom with different materials at the top. I'll quickly show a video as well, but before I show the video, if you'd like to see more of my work, you can follow me at Biolab Studio, and I actually sell those a few of the sculptures at biolabstudio.com. I'll quickly jump to the video. It should just take a minute. Okay, so what I'm about to show you now is basically a time lapse of the mycelium growing throughout the 3D printed scaffold that I was mentioning earlier. This was around a 2-week period. And it was just really quite fascinating to capture how the mycelium actually grows throughout the designated form. And here's the robotic tool that I mentioned earlier of that Arduino sensor. So on one side, we see the robotic syringe injecting the mycelium culture, and on the other side, we see the Arduino sensor monitoring the life of the organism. This was just initial tests that we've done in trays full of mycelium. And here's an image of the robot injecting the bioscaffold with the liquefied culture of the organism. And again, what I really like about this image is how delicately this interaction between the robot and the organism is. Again, when we think of robots, we think speed, efficiency, heavy materials, but there's really something really quite delicate between the biological growth and the movement of the robot. And here's just a close-up image of this was a lot of trial and error to see how exact we can get that syringe into the scaffold, because there was many, the robot completely knocking over the whole geometry. Many of those failed experiments. And then here we can see over time the mushroom starting to fruit, and then the robot acting accordingly to the mycelium's growth. And you can see the mushrooms here are actually pink. This is a specific strain that we've grown in Australia, trying to add different colours to the organism. Here's just a quick animation of the computational experiments that I was describing before, this idea of how to grow computational geometries. And here's just a quick view of the UR10 robot extruding the mycelium-based clay mixture. And here you can see how it just looks like regular clay, but over time the mycelium grows over the extruded form and almost like takes over the geometry. That's it. Thank you.